Hello everyone, my name is Yilei Liang. I'm an undergraduate student from King's College London. Today, I'm going to talk about PAIGE, which is Privacy Preserving Intelligent Personal Assistant at the Edge. Recently, more and more people start using personal intelligent assistant via their mobile phone or anything else. There has been some personal assistant invented such as Apple Siri, Google Home, and Amazon Alexa. However, we found that these personal assistants typically have some privacy issues. So let's first have a look at the intelligent personal assistant workload. In this diagram, we can see that for such IP assistant, the user can input their voice and an image. Then this data will be transferred to the IPA and then return the inference result to the user. The workload for such voice recognitions or an image recognition is more compute intensive than a standard Google search. The user can simply input some text. Therefore, for current IP assistant, we normally deploy them to cloud data center so that the performance is guaranteed. Although the cloud solution can have good performance as they typically have quite a lot of computational resources, the privacy will be an issue. We need to notice that some users' voice and image can be private. For example, in this case, we have the driving license, which can contain sensitive information such as their home address. The cloud provider can review such private data as long as we don't know what they are going to do in the cloud and what's their privacy policy. Let's see some data leaks examples. The first one, Google. They employ people to review voice recording taken by their assistant in order to train their assistant. However, in 2019, one of these employees leaked a large amount of recordings to a news in Belgium, which means now a lot of private data are leaked to public. Not only Google, Amazon Alexa, Apple Siri also have such data leak situations, which make people don't want to trust such IPA in the cloud to process such sensitive information. Even for this company, they declared they will keep the user's data private. So how about Edge? There are different conceptualizations of the Edge. It could be a data center in a city close to the user. It could mean the base station or street level cabinet serving the user, or even devices under the user's control. For users to be in control of their privacy, we need to have all private data in user-controlled devices. If we can move everything to the user's edge, as long as the data are processed at their own devices, which also means the user's data is now secured. That sounds good. However, we need to notice that these edge devices are typically not that powerful to hold an IPA locally, as we discussed before. An IPA include image recognition systems, speech recognition system, and another one, NLP and question answering, which typically have a large database. This database is too large to deploy on the user's edge. Let's go back to the cloud. We said that privacy has been an issue for cloud. So, can we preserve privacy in the cloud? The answer is yes. We can use encrypted computing, such as Intel SGX. Intel SGX allows the applications to ensure confidentiality and integrity, even if the operating system, the hypervisor, or BIOS are compromised. This also protects against attackers with physical access. Therefore, we can now trust the code executing it. Here's a simple diagram for encrypted computing. We have the untrusted environment at the left-hand side, the trusted environment, which is encrypted page cache for Intel SGX at the right-hand side. The untrusted environment first make a function call. It calls a trusted function. The code will be executed in trusted environment and then return the result to the untrusted environment. It seems that now we ensure the good performance as our system is still in the cloud, and the privacy issue is addressed by applying enclave computing. Well, is that true? Let's have a look at more details. This solution has some drawback. Here, we have another diagram showing how a single query is processed. We have image recognitions, speech recognitions, and NLP question answering system. This system normally required GPU. Unfortunately, currently there's no commercial release for enclave on GPU, which means this solution still cannot address the privacy issues of the cloud. Or we have to sacrifice our performance to run all these tasks on GPU to get the privacy, which is not a good solution. Here is our solution. We propose a hybrid privacy preserving IPA at the edge. To address the computation power limit at the edge, we add accelerators at the user's edge. This also addresses the privacy issues, as now the IPA is deployed at the user's edge so that they get the whole control of the system. We also keep our question and answering database in the cloud by using EnclaveDB. Let's have a look at the architecture. In step 1, the user submits queries. The query can include image, speech, or text input by user. Then, the queries are offloaded by PAIGE to one or more local accelerators. These accelerators are typically attached to some devices like Raspberry Pi under the user's control. After preprocessing, the output of the ML models will be sent to another device to do NLP inference, which is our step 2 and step 3. After that, step 4, this Raspberry Pi will send this NLP inference result to our enclave database. Finally, this database will return the question answering result to our user, which is our final step. Now, as we use edge accelerators to deploy our IPA at the user's edge, so that we get similar performance than cloud to ensure our performance. And as the whole system is at the user's edge, so the user get the whole control. So we also secure privacy. In our evaluation part, we focus on image recognition. We left speech recognition, question answering, and NLP to the future. What we measure? We measure ML performance, such as inference latency, Evans score, and etc. We measure the system suitability for real-time queries in terms of inference. And finally, we also look at energy consumptions. All these metrics we need to measure across the heterogeneity of devices and ML architectures, as there are many edge devices and accelerators and models at the edge. For hardware architecture, we use Raspberry Pi 4 with 4 GB RAM to be our gateway device. We deploy our benchmark on Raspberry Pi 4 CPU only, Raspberry Pi 4 with a new compute stick, and Raspberry Pi 4 with Edge TPU. To compare with these edge accelerators, we also deploy our benchmark on server class CPU and GPU. In these presentations, we focus on RPi 4 CPU, the second generation of new compute stick, i7 CPU, and NVIDIA 2080. For machine learning architectures, we use official MobileNet and Inceptions released by Google. In these presentations, we focus on MobileNet V1, Inception V1, representing for small image recognition model, and Inception V4, representing for large image recognition model. Here's our F1 score benchmarks. The x-axis is our models. We have MobileNet V1, Inception V1, and Inception V4. The y-axis is our F1 score. Regarding to the platforms, we have NCS, which use a model format called OpenVINO IR. We have TensorFlow Lite, HTPU model, and unquantized model. The model used by edge accelerators are typically being processed by sacrificing the F1 score to get lower inference latency, which will be discussed next. We surprisingly found that, apart from NCS2, the other models have similar F1 score compared with the unquantized model. Even they achieve higher F1 score in Inception V4. We believe the reason why is because of the bigger model of architecture such as the Inception V4, the unquantized process will not impact the F1 score that obviously. So here's the result of our inference time benchmark. Still, the x-axis is our models, and our y-axis is our inference latency. The unit is the milliseconds. We define two models for mode for servers: the default mode and the request mode. The default mode is that we inference multiple images in one single TensorFlow section, while in the request mode is like we start a new TensorFlow session every time we inference an image. We can see that the latency of request mode is much higher than the default mode, which means the overhead of starting a new TensorFlow is obvious. We can see that RPi4 with HTPU have comparable performance than the server CPU plus GPU in smaller models such as MobileNet V1 and Inception V1. For larger models such as Inception V4, the GPU still have better performance. Here is the energy benchmark result. The x-axis is different platforms. We have HTPU, then NCS, i7 Intel i7 CPU, GPU, i7 with request mode, and GPU request mode. The y-axis is energy consumed for inference a single image. We all know that GPU will normally consume more energy as they have higher power, but can also give you a higher performance as well. Therefore, we measure how much energy is consumed to inference a single image and obtain a specific similar F1 score. We surprisingly found that edge devices are most energy efficient across this platform. In particular, HTPU is the most energy efficient across these platforms, which is 0.015 joule to inference per image. So here are some takeaways. We first propose our hybrid solution PAIGE. We move ML tasks we don't process in the cloud to the edge by adding edge accelerators, and left QA database in the cloud by using enclave database. We also perform the benchmarks. We surprisingly found that Raspberry Pi plus edge accelerators has similar performance to CPU plus GPU. And they also have significant lower energy consumptions, which means more energy efficient. However, GPU still win for larger models, such as Inception V4 we mentioned before. And here's my email. You can also ask me anything after the workshop. And that's all. Thank you for listening. I'm happy to take questions here. Thank you.